In this video lecture here we will discuss about basis sets to be used in molecular quantum chemical calculations. To begin with here we remind that the basis set is needed since when we solve the electronic Schrödinger equation we usually rely on the Elkaut approximation, meaning that we expand each molecular orbital in a set of atomic orbitals or basis functions given an equation like this one here, meaning that we express the given molecular orbital as a linear combination of some set of simpler functions, namely the basis functions, which in our case would be the atomic orbitals, kappa 1, kappa 2, kappa 3, with given weights C1, C2, and C3 here. You also remember that we find the numerical value of these coefficients here, C1, C2, C3, by requiring that the total energy of the system is as low as possible. So in general terms, a basis set is a combination of mathematical functions that can be used to represent atomic orbitals, at least when we are to use a basis set in order to represent molecular quantum chemical calculations. So what we will be using as a basis set is this well-known set of functions comprising a 1s and the p and the d orbitals and so on. So first of all, we need here to define the mathematical description of each such orbital, that is a 1s and a 2s and the p orbitals and the d orbitals and so on. And one choice of this would be to use a Slater type orbital description of these atomic orbitals. Now the Slater type orbitals take this form given in this equation here. It contains a function describing the angular distribution, and then it contains another part here containing the radial distribution. And if you look at this here, you can see that it contains the exponential of minus zeta r. That is, we have an r to the power of 1 dependence in the exponent. Now these STOs here describe fairly well the radial electron distribution. However, a problem associated with using the STOs is that these are very difficult to handle numerically because integrations cannot be calculated out using analytical expressions. So, in fact, we only use such STOs in very limited cases. Another choice of basis functions here would be to represent the atomic orbitals using Gaussian type orbitals or GTOs. Now, compared to the STOs, we have the same form of the angular dependence here in the atomic orbitals, but the radial dependence here is different. Especially here we have in the exponent for the exponential function not a zeta times r to the power of 1, but we have a zeta times r to the power of 2. This is why we call these functions for Gaussian type orbitals here. Now the Gaussian type orbitals describe in fact less satisfactory the radial electron distribution. If we look at a curve here of a Gaussian type orbital, then this curve here becomes too flat for very small values of r, and also it drops off too large as we increase r. And this is due to the fact that we have this r to the power of 2 dependence in the exponential in place of the r to the power of 1 dependence in the exponential. However, from a computational point of view, the Gaussian type orbitals are very easy to handle because integrations can be carried out using some closed form and some analytical expressions. So the GTO is actually the common choice of basis functions to be used in electronic structure calculations. We could of course say that, well, these basis functions, the GTOs, do not represent the radial electronic distribution in the molecule or in the atom well, so it is not good to use those. But in fact, what we can always do here is that we can approximate a given Slater type orbital by a linear combination of a number of Gaussian type orbitals. So let's try to illustrate this here. In this first figure here, we have plotted in the red line here a Gaussian type orbital, and on top of this we have plotted the corresponding Slater type orbital. And you can see that, well, for sure these two curves here deviate. They have a region where they are reasonably similar, but then the red curve becomes too flat here, and it also drops off too fast as we increase the value of r. Now what we can do here is to make a linear combination where we combine two Gaussian functions, and now we plot this linear combination of two Gaussian functions, and we can see that we get very improved behavior compared to the Slater type orbital. If we combine three Gaussian type orbitals in a linear combination, then we actually can reproduce the Slater type orbital to a very high degree of accuracy, as we see here in the picture to the right. So it means that even though the Gaussian type orbitals actually do not represent as accurate as the Slater type orbital the radial dependence of the electronic density, then what we can do is just that we can use more of the Gaussian type orbitals in order to actually get a very accurate representation of the electron density radial distribution, meaning that if we used a basis set consisting of the Slater type orbitals, then we could use fewer functions, but it would be difficult to handle the integration related to those functions. Or we could use Gaussian type orbitals, and here we would need to have a higher number of basis functions included in our basis set, but on the other hand the computational costs would be less due to the fact that here we can carry out the integration analytically. So the latter choice is usually what we made in electronic structure calculations. Now if we look here at specific basis sets for atoms or molecules, then we define the simplest basis set that we can use as a minimum basis set. And this is a basis set that contains only enough functions in order to accommodate all the electrons. So if you have, for example, a carbon atom, then this would contain a 1s function, a 2s function, and 3 p functions, giving a total of 5 orbitals that we use in order to accommodate these 6 electrons that we have in the carbon atom. The minimal basis set, of course, do not adequately describe the anisotropic electron distribution in molecules. It is simply too simple. So what we do is often that we improve upon the minimum basis set by using a so-called double zeta basis set, which has 2 sets of functions but of different sizes of the radial distribution that allows for more flexibility. So if we go back here to the form here of the Gaussian type orbital, then we can see that we can actually make the Gaussian orbital here go towards 0 either faster or slower by simply choosing another value for the exponent zeta up here. So if we choose zeta here to be a small number, then the radial distribution here will go towards 0 very slowly, and if we choose the zeta value to be a very large number, then the function will drop to 0 very quickly. So what we do here when we talk about a double zeta basis set is that we simply double the number of functions that we find in the minimum basis set. But in this new shell of basis functions, we of course choose the exponent to be different from in the original shell. This of course gives much more flexibility when we are to describe the molecular orbital using an expansion in this basis set. This concept can be generalized to having a triple zeta basis set, a quadruple basis set, and so on, meaning that we triple the number of functions, we have 4 times the number of functions compared to the minimum basis set using a quadruple basis set, and so on. So for example, for the double zeta basis set for the carbon atom, we would have 2 1s functions, we would have 2 2s functions, and we would have 6 2p functions. The 2s functions would have different exponents, the 2 2s functions would also have different exponents, and we can group the p functions into 2 groups, and in each of these groups here, the p functions will have different exponents. Now often we invoke what we call a split in this, for example, doubling of the basis functions, meaning that we only double the number of basis functions for the valence orbitals. This is because it is the valence functions that are chemically important. So for example, if we again go back to the carbon atom in a double zeta basis set, then we would have only a 1s function, we would have two 2s functions, and we would have 6 2p functions. That would be a double zeta split basis set. We will talk more about the basis sets when we actually do the calculations at the computer exercises later on. For the double zeta basis set, we can illustrate this using this picture here of the HCN molecule. Now, using a double zeta basis set, we now have the possibility of having p orbitals in the bonding here to be more compact compared to p orbitals that are out of plane with respect to the bonding. If we used only a single zeta basis set, then we would have to have the same electron distribution. That is, we would have to describe the electronic distribution using the same set of functions in this direction here and in this direction here. But using a double zeta basis set, we gain much more flexibility. In addition to doubling, tripling or quadrupling the number of basis functions in our basis set, we can also include other kinds of special basis functions. We term a special class of basis functions as diffuse basis functions, and this class of basis functions represent a basis function which has a very little value for the exponent zeta, meaning that this is a function that will drop towards zero only very, very slowly. Now these functions here are important to be used if we have molecules that have electron distribution far away from the nuclei. This could, for example, be molecules with lone pairs, it could be if we are to describe excited states, or it could be if we are to describe, for example, anions. So in this case here, we have the hydrogen atom. It has an electron distribution like this. If we add an electron, then we get a more diffuse state of the hydrogen atom, meaning that we would need to include the so-called diffuse basis functions in our basis set. In addition to the diffuse basis functions, we can also include what we call polarization basis functions. And by polarization basis functions, we mean higher angular momentum functions that can be used in order to improve the description for the anisotropic electron distribution. We do this in the way here that we normally add p orbitals to hydrogen and d orbitals to first row atoms, f orbitals to second row atoms, and so on. And remember here that, for example, for the first row atoms, we do not have any d electrons in our in these molecules or in these atoms, but we add d orbitals in order to allow flexibility. By flexibility here, we mean that by adding the p orbitals, we actually allow for the p orbitals to become polarized. And this can be described by including higher angular momentum functions, that is d orbitals, in the basis set. We can illustrate this here again for the case of HCN. Now, if we don't have any polarization functions on the hydrogen atom, then this would be fairly spherical symmetric here. It means that we cannot model any anisotropic distribution on the hydrogen atom using a basis set with no polarization functions. But in reality, we would expect the charge distribution on hydrogen here to become perturbed by the electric field created by the atoms here, by the electrons on the nitrogen and the carbon atom, meaning that we would expect the charge distribution here to deviate from something being spherical symmetric. We can allow for this by including on hydrogen a set of p orbitals in the basis set, meaning that we can now, using these p orbitals, that is higher angular momentum functions, we can allow for the electronic distribution to deviate from being spherical symmetric. So this is why polarization basis functions usually are quite important. Finally, here's a list that I have compiled of some of the most common basis sets to be used in electronic structure calculation, and as you can see we have quite many, and these are only examples of basis sets. So the point being here, it is quite important to be able to look at the code for a given basis set behind each of these lines here. CCPV5 set, I think it says here, is a specific combination of functions. And it is very important that we are able to look at these codes here for the basis set combinations and then to choose a basis set that actually fits into what we are going to do. For example, if you are to do calculations on anions, on excited states, or some molecules which have many lone pairs, then usually we would need to choose a basis set that contains diffuse functions, and so on. So at the computer exercises we will be talking a bit more into how to actually choose a proper basis set from this list of basis sets here and to use this basis set in the electronic structure calculations.